Okay, so let's continue from where we had left last time. If you remember, we were discussing about packet switched networks and how real time communication can be supported in these networks. So, we had looked at resource reservation and we had looked at rate control. These two things we had looked at last time. So, we were trying to discuss the service discipline, and we were saying that the traffic becomes distorted as it proceeds in the network, and the service discipline's responsibility is to reshape the traffic to its original characteristic. So, let us proceed there from that point. So, the service discipline we had said is can be thought of as a queue. In this queue, packets from various connections reside, and this typically on the outgoing link, and there is a scheduler. The service discipline includes a scheduler and this buffer. So, the buffer has the different packets from various connections, and then the scheduler selects a packet to be transmitted on the outgoing link based on the resource that has been reserved for that connection. So, in simple words, we can say that the service discipline is the mechanism used to schedule incoming packets for transmission, where we look at the resource that is reserved. The service discipline examines the resource that is reserved and also to reshape a distorted traffic. And the rate based service disciplines are used to and these help prevent fluctuations due to network load or to reshape the traffic. The sources of the problem is the load fluctuation which cause the abnormal instantaneous rate even from well behaved sources, or in other words, in simple words, a traffic becomes bursty even when it is well behaved at the sources. As the traffic passes from one switch to other, it becomes more and more bursty, and the service discipline helps to tackle this. So, we can think of one responsibility of the service discipline is distortion control in the traffic characteristics. So, the service discipline will reconstruct the traffic to its original characteristic at every switch. And we are trying to examine the extent to which a traffic can become bursty after it is transmitted over a switch. The worst case traffic before the ith switch will become sigma plus delta sigma, where sigma is the burst size over the average traffic rho, and delta sigma is summation of I is equal to 1 to I minus 1 rho into dj max. Okay, I should have said j equal to 1 to j equal to I minus 1 and rho into dj max, where dj max is the delay bound for the nth switch, sorry jth switch it should be. Dj max is the delay bound for the jth switch. So, this we had already seen, just I had drawn this to help you understand what we mean by sigma and rho. Sigma is the average traffic. So, the number of packets per t time units will be sigma into t, and the burst size is given by sigma. So, we can think of a service discipline to include a rate controller or distortion controller and a scheduler, which transmits packets from different connections based on the resource reservation. So, there are two main responsibilities of a service discipline. One is the rate controlling and other is scheduling. I have already seen that. Now, let us see what are the service disciplines that are being used popularly. If we look at that, we will see that there are two main types of service disciplines that are being used. One is called as the work conserving discipline and the other is called as the non-work conserving discipline. Now, let us examine what are these two types of service disciplines. First, let us look at the work conserving discipline. In the work conserving discipline, a server is never kept idle if there is a packet to be sent. This is the service discipline, we are calling it as a server. So, the server will not be idle. If there is a packet to be sent, it will send it out. It cannot be the case that the server is idling and there is a packet is waiting. Of course, if the link is busy, then the packet will be queued, the server cannot send it out. And in a work conserving discipline, no traffic shaping is achieved, because it does not delay them unnecessarily, right. If the link is free, it will transmit them. A work conserving discipline does not reshape traffic.
The shaping is required only when traffic becomes distorted.
Yeah, traffic becomes distorted naturally in every packet switch network. So, if we have all CBR traffic, there is no burst in the sources at all are transmitted at a CBR constant bit rate, and also there is no non real time traffic, then it will not become bursty.
So, this is applicable for CBR kind of.
Okay, we can think of that wherever rate control is not a matter of concern, we can use a work conserving discipline. So, the examples of a work conserving discipline is weighted fair queue, multi-level FCFS queue, delay EDD, the names of some popular algorithms. Now, on the other hand, a non-work conserving discipline, here even when the packet has come and got queued, there will be an eligibility time assigned to the packet. Only after the expiry of the eligibility time, the packet will become eligible to be transmitted. So, it is possible therefore, that an outgoing link can be idle and there are packets waiting, but nothing is getting transmitted, right, because none have met their eligibility time requirement. So, here also there are many algorithms or service disciplines based on the non-work conserving discipline, for example, Jitter EDD, stop and go, etc. So, we will discuss few of the important ones. The type of the service discipline, whether you are using a work conserving or non-work conserving, would depend on how much you can tolerate delay, what about the buffer requirements at the switches, the tolerance of the delay jitter, and so on. The work conserving disciplines need less buffer space and cause shorter delay than the non-work conserving discipline. Why is that? Yes, anybody would like to answer? This is a claim we are making, that the work conserving disciplines need less buffer space at the switch, and this cause shorter delay than the non-work conserving discipline.
Naturally, it will not buffer unnecessarily.
Yeah, it does not delay them unnecessarily, that is the answer. It does not delay them unnecessarily. So, definitely the buffer requirement will be lower then the non-work conserving discipline, and also since it delays them to a lower extent, the total delay will be less, isn't it? Simple thing. Okay, let us proceed. Another claim we are making here is that the work conserving disciplines cannot bound delay jitter to any requirement, whereas the non-work conserving discipline can. What about this? The work conserving discipline cannot bound delay jitter to any agreed quantity. So, the delay jitter can become very high, while a non-work conserving discipline can bound the delay jitter. Do you agree with this? If you agree, then you will have to justify why this is the case. Yes, anybody would like to tell anything about why, I mean this specific claim that a work conserving discipline cannot bound delay jitter tightly, while the non-work conserving discipline can. Can anybody try to justify this, or can try to say that this is wrong?
In NWCD, it assigns a time delay to every packet.
Yes.
And so that is why it is controlling the time delay of that.
No, it is making it more delayed, that is all. But what about delay jitter? We are talking of delay jitter.
So, at its will, it can make it more tightly bound or not.
Not really. So, let us see why it is. Anybody would like to tell any other answer? Okay. Let us see why that is the case. See, if there is the traffic is bursty, okay, the traffic has become bursty. We had said that in the work conserving discipline, no traffic rate control is achieved, just transmits, right. So, it is possible, depending on whether it is in a burst and has got queued or not, it can take different time to reach the destination. So, if it is just following a burst, it will take long time to reach the destination, longer time. But if it is come when there is no burst, it will reach faster. Okay. But whereas in non-work conserving discipline, we are trying to make the traffic not bursty, right. We are controlling the burst size. So, the amount of jitter will also be less. So, the amount of time a packet will have to wait at a switch is almost constant, whereas in the other case it can either wait for a long time or can get transmitted quickly. Does that appear convincing? Okay. So, in a non-work conserving discipline, the arriving packets, they are queued, and then there is a eligibility time computation, and based on that they are sent to a demultiplexer, where they are transmitted on different queues based on the service, based on their reservation, and from there they are transmitted on the same link. So, the different connections they are queued here and transmitted over here. Now, let us look at rate conserving, a work conserving service discipline. The name is multi-level FCFS queue, a popular work conserving discipline, and it is used to implement static priority schedulers. So, here the different packets or different connections have given different priorities. Each level of the queue corresponds to a different priority level, and naturally each connection is assigned a priority, and two connections may even have the same priority. And depending on the priority of the connection, it is inserted in the corresponding FCFS queue. Multiple connections even can have the same priority. The packets, once they are queued in the FCFS queue, just follows the FCFS order, and from the highest priority queue the transmission begins. If there is no highest priority, the queue is empty, then it will be the next that is taken for transmission. So, here how does the priorities get assigned? The priorities are get assigned by the different delay bounds that have been promised to the different connections. So, the number of delay bounds that can be promised to different connections depend on the number of priority levels, number of FCFS queues that can be supported. So, here just see that they are just queued in different queues depending on their priority, and then they are just taken up as soon as they are available, right. So, there is no waiting time involved here, unnecessary waiting time, right. As soon as the link is available and there is no higher priority packets to be transmitted, they are transmitted, right. Okay. Now, let us look at the weighted fair queuing. This is another algorithm, multi-level FCFS queue, very simple algorithm. The weighted fair queuing, let us look at it. It has evolved from a popular algorithm called as fluid fair queuing. So, for all the connections sharing the link, there is a separate FIFO queue. So, as many outgoing links are there, that many FIFO queues will be there. And during any time when there are exactly non-empty n non-empty queues, the server serves n packets at the head of the queue at the rate of 1 by n of the link speed. So, what it says is that if the FIFO queue for one link is non-empty, then it will transmit at the rate of n packets that are at the head of the queue at the rate of 1 by nth of the link speed. But that was a simplistic thing that we said, that it just transmits n packets at the front of the queue. Actually, it allows different connections to have different service shares. So, the service shares of different connections are given by phi 1, phi 2, phi n. Now, if B is the set of non-empty queues and C is the link speed, then the service rate for a non-empty queue is phi I by sigma phi j into C. So, what it means is that for every connection on a link, its share will be C into the reservation for it divided by reservation for all others. So, it serves packets according to their service shares, and there are two main assumptions, that the server can serve all connections with non-empty queues simultaneously. So, the n packets, each one with 1 by n if there are equal reservation, or depending on the phi they will be transmitted. And another assumption is that the traffic is infinitely divisible, but we know that packet sizes are discrete. So, the FFQ in its exact spirit is impractical, because it is based on the fluid transmission, right. Data is discrete, isn't it? It is not really a fluid. So, in the exact implementation of FFQ, it is impractical, because traffic is not infinitely visible, these are discrete. But of course, with an approximation we can implement the FFQ. Now, let us look at the jitter earliest due date. So, here when a packet is served by one router, a field in its header is stamped with the difference between the deadline of the packet and the actual time at which it is transmitted. And once it reaches the next router or the next server, it holds the packet for this period, which is its eligibility period, and it provides delay jitter bounds. So, this is the explanation of this. See here, at every switch there is a delay bound. Okay. So, the delay bound for every switch is fixed. The total delay between for the packet that was agreed during the connection is distributed among different switches. Now, as it arrives at a switch, it is taken up for departure, but it should have been transmitted at this point. I mean, its deadline that was allotted for this switch, maximum deadline was this point, right, but it was transmitted here. So, this is called as the pre-ahead time, before which it got transmitted. So, this is stamped here, the actual time at which it should have departed, I mean the maximum delay that should have encountered here, and then the time at which it actually departed, these are stamped on the packet. And as the packet comes to the next switch, the ith switch, it is held for that time. It arrives and then it becomes eligible only after the maximum time it should have waited there. Now, again there is a delay bound, and it might get transmitted sometime here, and in the next switch that will be taken care, right. So, it provides a good bound on the jitter. Now, let us look at the stop and go. The stop and go algorithm is based on the multi-level framing strategy, but first let us consider the one level framing, and if we understand this, then we can extend it to a multi-level framing, because if we first start discussing about multi-level framing, it might appear a bit confusing. So, let us look at the simplest case of a one level framing. In a one level framing, we divide the time axis into frames. Each frame is of size t. T is also called as the average aging interval, also called as the frame, and T is a parameter for the one level framing.
What do we mean by aging?
The aging interval is the time they would have to wait. They would have to, the packet would have to age there before it can get transmitted. Now, each connection is allocated a bandwidth in proportion to a certain fraction of the frame time. So, there are different connections for a link. Now, the link has certain bandwidth which will be distributed among all these different flows or connections. And if you think of it, then the frame time t, over frame time t, it has to be transmitted, right. Once it comes, it ages for t, right, it waits for t, and then it gets transmitted in over the next frame. So, for the next frame, there will be a certain fraction of the time which has been allotted to it, it will be transmitted during that time, right. So, this get delayed by a theta which depends on the t actually, which is less than t actually, the theta is less than t. Now, a packet that arrives for a link L during a frame F, sometime during this frame the packet arrived, it will be delayed until the next frame. Now, even if there are packets that have got delayed and nothing is getting transmitted on the link, it just waits for the next frame to start. So, a packet that comes in one frame can get transmitted only in the next frame, and till that time it idles, and then once the new frame starts, then the portion of the time that has been allotted for that connection, it has to wait till that time and then get transmitted. So, the one level framing strategy introduces a delay which is bound maximum by 2 frames, 2 frame times, because in the worst case it can arrive at the beginning of a frame and possibly the time it could be transmitted or which was allotted to it was the end of the next frame. The worst case, the packet, the delay of a packet at a switch is bound by 2t. But see, t, if it is large, then the delay can be unacceptable for a connection. So, a smaller t is desired. Now, assuming that a packet has a fixed size p, then the minimum granularity of the bandwidth allocation is p by t, right. So, see, t is the time that is available to us to transmit all packets. So, one packet will take how much time to be transmitted? P by t. So, to have more flexibility in allocating bandwidth, a larger t is preferred, but we saw that if the minimum granularity is p by t, so inversely proportional to t, right. On the other hand, if we have flexibility in allocating bandwidth, that is granularity, a larger t will be preferred, because if we can transmit only let us say a few packets in each frame, then we are losing flexibility, is not it? How many packets for each frame we can allocate? We can't allocate 1.5, is not it? We will have to allocate in integer number of packets. So, there is a conflict here. On one hand, we want t to be increased, and on the other hand, we want t to be reduced. So, that is what it says, a low delay bound and a fine granularity of bandwidth allocation cannot be achieved simultaneously in the stop and go scheme. So, either you should agree to a larger delay on the packets, the end to end larger end to end delay in the packets, or you have to compromise with wastage of bandwidth, because the granularity is low and bandwidth will get wasted, because you can give a fraction of a bandwidth to a connection. The multi-level framing is actually an extension of the single level framing. The time axis is divided into a hierarchical frame structure, T1, T2, Tn, etc. And Tm plus 1 will be some Km into Tm. So, these are integral multiples of each other. Each of the frame Tn may be 2 into Tn minus 1 or 3 into Tn minus 1 and so on. Now, a packet on a level P frame, the Tp, they use the frame size Tp, right. So, if we assign a packet to a frame size to level P, then they will always use the frame size Tp. There may be some other packets which will use frame size T1, some may use Tn, but some connection might use Tp. So, the level P packets which arrive at an output link will become eligible in the next frame, next Tp frame, the same thing. So, for the T1 frame, the packets which are using the T1 frame, once they arrive, they become eligible in the next T1 frame, and those in the Tn frame, they will become eligible in the next Tn frame. So, the one that are assigned on the Tn frame will undergo higher delay, isn't it? The packets that are on Tn frame, or the connection that has been assigned the Tn frame, will undergo higher delay than the one that have been the connection that has been assigned the T1 frame. But if the delay is permissible, then we can assign to Tn, and that will increase the network utilization, isn't it? So, this just says two level framing, where we have two frame sizes T1 and T2, and T2 contains 3 T1s. So, some packets which are assigned to some connections that are assigned the T1 frame will undergo a maximum delay of 2 into T1 at this switch. The one that have been assigned to the T2 frame will undergo 2 into T2 delay in the maximum. So, depending on the characteristic of the connections, we can assign them to the different frames. Now, one thing is that the ones we so far discussed, both the work conserving and non-work conserving, is that they are rate controlled. What about the one that we discussed just now, the single framing and multi-level framing? Is that a work conserving or a non-work conserving discipline? Let me just ask at least this question, simplest question. So, you will have to think that what is the definition we gave for a work conserving discipline versus a non-work conserving discipline, and whether it satisfies that one. I mean, it satisfies which one? Okay. So, he says non-work conserving. What about others? No answer, is it? Let us hear his answer. Why you are saying it non-work conserving? Exactly. So, the definition of a work conserving and non-work conserving is that in a work conserving, the packet is not made to wait unnecessarily if the link is available. In a non-work conserving, the packet has certain eligibility time, and till that time, even if the link is available, it will not be transmitted. And we had seen that a non-work conserving discipline bounds the jitter. So, here in the framing strategy, it said that a packet as it arrives becomes eligible only in the next frame. So, it has to wait until the frame gets over, right. Even if the link is idle, it will have to wait, and therefore, it is a non-work conserving discipline. Okay. Now, the drawbacks of the disciplines we discussed, all of them were rate controlled disciplines. So, one is that they are difficult to implement. This framing strategy has the problem that there is a compromise between the queuing delay and the granularity of bandwidth which can be allotted to a connection, because again, if you think of it, it has its origin in some fluid flow, right, where you can even have a small granularity flow occurring, but here a packet can be 1 kilobyte or several kilobytes of data that need to be transmitted. Now, we will discuss about RCSP. Here we will see that the rate control has been decoupled from the delay control. So, in the disciplines that we discussed so far, all are based on rate control, but and we saw that each of them have some difficulty. Now, let us look at one algorithm called as RCSP, where the rate control and the delay control have been decoupled. As the name says, there are two components here. One is the rate controller and the other is the static priority scheduler. The rate controller consists of a set of regulators for each connection. Now, the regulator is responsible for shaping the input traffic to the desired pattern, and when a packet arrives, its eligibility time is calculated and the eligibility time is written on the packet. So, the rate controller is implemented through a set of regulators. The regulator will examine the packet as it arrives and it will mark it with a eligibility time, and the regulator will hold it until the eligibility time expires. Again, see, just check here that all traffic shaping are based on delaying the packet in some queue. Now, once the eligibility time has expired, the regulator hands it to the scheduler for transmission.
Similar to that work, non-work consuming.
Not really. See, there every packet is just arrives, and depending on the frame at which arrives, it just undergoes some delay until its turn comes.
Also, you assign that some time to it.
No time is assigned. See, the frames are fixed. See, in the multi-level framing, the frames are fixed.
Age interval
So,
you are assigning that.
the frames, that those are the aging interval or the frames, and depending on wherever it appears, it just gets transmitted on the next frame. But there is no rate controller as it is, which will based on case to case delay it, right. So, here it will examine depending on the condition for that connection, it will delay to varying extents. So, there it just the frames were fixed, and depending on where it arrived in the frame, it can get transmitted only in the next frame automatically. There is no role of a rate controller there, it happens automatically. Automatically, and we can think of that it is just a rate based transmission, where a packet becomes eligible in next frame and a rate or a bandwidth is assigned to it and it gets transmitted during that time, right. So, let us see here. So, the scheduling algorithm here is a multi-level FCFS queue and serves packets in order of their priorities. So, as far as the scheduler is concerned, nothing too much to discuss here, but the regulator can be two types, the rate jitter or a delay jitter type of regulator. A rate jitter type of regulator, it will examine the connection, the packets that are coming from the connection, and it will try to reconstruct the traffic partially. Whereas a delay jitter, it will control the delay jitter by fully reconstructing the traffic. So, we will not really go into the details of how it does the rate jitter, how much does it delay, what do you mean by partial reconstructing, etc. We will not go into this, but here what we need to understand here is that there is a separate component called as the regulator, which will look at the traffic. See, earlier in a framing, it never had any analysis of the traffic, it just delays them by that amount. Depending on where it arrived, it automatically gets delayed till the next frame, but here it keeps track of the traffic, and depending on the current traffic rate, it will either partially reconstruct the traffic or fully reconstruct traffic, depending on what type of regulator we are trying to use. So, this is a more sophisticated form of service discipline as compared to the simpler service discipline, the rate based ones. So, there are different regulators which keep track of the traffic, and then they transmit it to the scheduler after they have reshaped the traffic. Now, let us look at the quality of service models that have become popular in the internet. So far, we just looked at the components of a quality of service framework that can be used to provide quality of service guarantees. Now, let us see, in the internet there are some standards that are emerging. The standard is proposed by IETF, the Internet Engineering Task Force, if I am not wrong, this is the full form, the Internet Engineering Task Force. This is the standards body for the internet, and this has proposed 3 major quality of service models. One is called as the integrated services or the IntServ, the differentiated services are the DiffServ, and the multi-protocol label switching or the MPLS. So, these have because these have been proposed by a standard body and are applicable to the internet, they have drawn lot of attention. Even in a literature that you read in any other book, you might come across these terms, and even on a newspaper you can come across these terms. Let us look at the basic idea behind IntServ. IntServ is a protocol that has been designed to support both real time and non-real time traffic in the internet. Naturally, it extends the internet protocol such as IP, and it is a per flow based quality of service framework. What it means is that for every connection it keeps track of several information. It is a per flow based quality of service network. So, that is for every connection it stores several information all through the internet, all through the routers that are concerned, and it uses the RSVP protocol for dynamic resource reservation. We know what is RSVP. And for the real time traffic, see the non-real time traffic, they operate as the internet is operating right now, but for the real time traffic there are 2 service disciplines. One is called as the guaranteed service discipline. Here the service discipline would provide an upper bound on the end to end queuing delay, and these are the guaranteed service discipline would be used for real time communication, hard real time communication, whereas there is another service discipline which provides statistical guarantee only, that is what will be the average delay and so on, maximum delay, average delay, etc.
Even in internet, do we have hard real time?
See, I am not talking of the that IntServ has been implemented in the internet that you are using right now, but it is a standard which can be used in future. We will see. I mean, first let us look at its pros and cons and then see whether it will be used.
I'm just asking whether
Right now the internet that we are using, it does not support hard real time traffic, but if we have IntServ implemented on that, on the internet, we will see the complexity of implementation, and if IntServ is implemented, then it would be possible to do hard real time applications on the internet.
like people are talking about remote medical
Exactly, remote medical monitoring of a patient on the internet, or let us say you have some embedded devices which you are giving remote commands controlling that, it would become possible. But let us see the complexity of implementing the IntServ. So, one complexity is that the amount of state information increases if you have large number of real time connections, because we had seen that it is a per flow connection and the information has to be maintained every router. It uses the RSVP, and RSVP we know that the state information need to be maintained, isn't it? The reservation information and the path information need to be maintained at every router for every connection. So, this is one complexity, that the information that need to be maintained at the router can become enormous depending on a number of real time connections that need to be supported, which can place a huge overhead on the storage and processing on the routers. And then the present routers that are there throughout will have to implement RSVP, admission control, packet classification, etc. So, it would be difficult to implement it, isn't it? Because not only that, there are large number of information that need to be stored depending on how many real time connections are to be supported, but also you will have to change all the routers now. They have to implement RSVP, admission control, packet classification, etc. And universal deployment or ubiquitous deployment of IntServ would be required for a guaranteed service. So, all through the millions or billions of routers are there, they have to implement all these things, RSVP, admission control, packet classification, and then the amount of information they would have to store is huge, and certainly a non-trivial task. To in any time sooner you will get all these things working on the internet looks difficult, and not only that, incremental deployment of IntServ is also difficult. Either you go for it fully or you do not go for it, right. So, the IntServ has its limitations, and we have understood the limitations, isn't it? Why it would be difficult to implement IntServ on the current internet and get it to support real time communications. Now, let us look at the DiffServ. The DiffServ does overcome some of the limitations of the IntServ. One is that it is simpler, less information needs to be maintained, more scalable. So, the way it would work is that it would redefine the type of service field in the header of the IP4 or IP6 packet. In the type of service, it will have a differentiated service field, and the first 6 bits in that, as it has been proposed by the IETF, the first 6 bits are called as the DS code point, and there some information will be stored on the packets. So, the router does not have to maintain any information, very important. I mean, the IntServ and DiffServ, the scalability of the DiffServ arrives because it just stores some information on the header of the packets rather than storing large amount of information on the routers or the switches. So, here the required information is carried out, the buffer management, scheduling, all these are carried out in the packet. The information is stored in the packet, and there is no special protocols and storage information at the routers. And the amount of information that only the switches have to store now is depending on how many service classes we wish to support. For each service classes, the switch or router will simply have the information is to how to handle that packet. A packet is based on the class 10 or class 5, how does the switch or router handle that? So, just see here that rather than storing information compared to the number of application flows, which can be 100 or 1000, here it just need to be store information of how to handle that particular packet belonging to a class, which can be 6, 10 or 20 maximum. And another important principle, see, one we saw is that the information is not stored on the switches or routers, it is distributed on the packets. The other important principle behind the design of the DiffServ is that the kind of processing that is required is only done at the network boundaries. Only the edge routers are responsible here. The core routers, packet as it gets transmitted might undergo transmission through several large number of core routers. So, if every packet from every connection need to be processed by the core router, it has to examine the kind of class that it belongs and do differently for it. That will be a very large overhead. But here it is trying to restrict the processing to only the network boundary, only at the host and the edge routers. And this is scalable because the edge routers handle only small amounts of flow. The core routers, they carry flow from all possible applications that can pass through it, but the edge router is only for those hosts that are connected to it. Those are finite in number, and therefore, the edge routers can easily perform tasks like packet classification, traffic conditioning as compared to core routers. So, there are two service models in the DiffServ, just like in the IntServ we had seen two service model, the guaranteed and the best effort service, I think the statistical guarantee and the guaranteed service. Here there are two service models again. One is the premium service, which is a guaranteed service optimized for regular or constant bit rate traffics, and these traffic which in the premium class, they undergo almost no queuing delay at the router. So, it becomes almost like a virtual leased line. The internet behaves as if it is a virtual leased line, and the assured service class, it provides statistical guarantees to application just like IntServ. So, we have just looked at the summary of IntServ and DiffServ. Those who are interested can look details, just discussed only the very essential features. Now, let us see how soft real time communication can be provided in a LAN environment. So far we have been looking at the hard real time applications, and then we had looked at hard real time applications in the internet. Now, let us look at the soft real time applications. Here no absolute quality of service guarantees are needed by the applications, and only we need prioritized treatment based on what class they belong to it, what class they belong to. We need to keep the message deadline miss ratio to a minimum for this kind of classes. So, some of the assumptions that we will make here is that the soft real time traffic are either CBR or VBR, and the soft real time message rates are very low compared to the channel capacity, and these can arrive periodically or in bursts, and in the presence of burst it becomes difficult to sustain the guarantees. So, there can be misses for soft real time traffic, and the way that it works is by smoothing the effect of the burst, just like we had seen the leaky bucket. Similar things happen here. So, here one of the popular technique is by Sin et al. It takes into account the limits of the transmission capacity of the network, and it uses a traffic smoother in the MAC protocol of a LAN, and the traffic smoother actually uses a leaky bucket algorithm, a variation of the leaky bucket algorithm called as the credit bucket depth. Small variation, we will just look at it, but since we are running out of time and we need little bit of time to discuss this, we will just stop here. We will continue in the next class. Okay, thank you.